right, class, so today we're going to talk about Chapter 10. Chapter 10 is the last chapter we cover in this class, and it's going to cover some types of tests we can use, some different scores that we can find in order to determine, in order to prove a hypothesis test. So those are going to be, previously we've been working with z-scores. Now we're going to look at t-scores, so t-tests, chi-squared, and then finally a NOVA, that stands for analysis of variance. So why don't we get started with section 1, where I'm going to talk about the t-distribution and what that means. So, like I said, in previous chapters, we would find z-scores or confidence intervals when we did not know the population's standard deviation, right? We would go ahead and find the z-score, we could calculate a confidence interval, and this would give us estimations about our population's standard deviation. The problem is that this can cause errors. This blue doesn't really show up. The problem is that this can cause errors. So we want to use a better approach, and this is going to be a t-distribution. Now, we've heard this word distribution before when we're talking about a normal distribution. So when do you use a t-distribution versus a normal distribution? So normal distribution, you want to use when your standard deviation is known and the population is normally distributed, or the population size is greater than 30. You use a t-distribution when you do not know your standard distribution and your population is normally distributed, or your population is greater than 30, okay? Note, at this point in time, and in this class, if the population isn't normal and your sample size is less than or equal to 30, neither of these distributions can be used. So, the t-distribution is also called a student's t-distribution. And as t increases, it gets really, really close to the normal curve. So as our sample size increases, you can kind of see here I have an n equals 3, n equals 12. It gets really, really close to the standard normal distribution. But this is something we can calculate without knowing the standard deviation. So I calculate a confidence interval the same way we did before, except that before we had our 1.96, which came from the z-table. Now we have our t-value times the square root of n, okay? Now, what is a t-value? We're going to see in the next slide. But to calculate the error, we take error equals our t-score times s, which is our sample standard deviation. Before we had sigma, right? Our population standard deviation. Now we have our sample deviation over the square root of n. Now, finding t-values is a little bit different. So let's take a look at what a t-table is. So first off, here's a table of critical t-values. As you can see, there's something called degrees of freedom. And then it's broken down by the area in 2 tails or the area in 1 tails. Notice we're only using a 0.05 significance test when it comes to t-values. That's going to be the case. Another thing, we only use this for sample means, because we can still calculate a z-score for proportions without the standard deviation, right? That's not something we're given. So in order to find a critical t-value, we need to know whether we're doing a 2-tailed or a 1-tailed test, and we need to know our degree of freedom. Now, the degrees of freedom is the sample size minus 1. And as you can see, this table goes all the way up to 40, and then it counts by 5s, and then 10s, and then a couple hundreds. So you're going to want to pick the value closest to what you get. So if I had a population of 110, my degrees of freedom would be 110 minus 1, and my closest critical t-value would be right here in this row. So let's start using this table. So again, here, like I talked through, are our steps for finding the t-value, okay, First thing you need to do is identify your degrees of freedom and then your area in one or two tails. We're going to use the area in two tails because our margin of error can be either above or below the mean when we're calculating a confidence interval. Okay? So, here are 5 measures of diastolic blood pressure from randomly selected adult men. These 5 values result in the sample statistics n equals 5. Our sample mean is 69.4 and our sample standard deviation is 10.7. So using this sample, I want to construct a 95% confidence interval estimate of the mean diastolic blood pressure level for the population of all adult men. So the first thing I knew, okay, is that my sample size is 5. My sample mean is 69.4. And my standard deviation is 10.7. So in order to calculate my error, which is going to be our t-value times s over the square root of n, this is my s, I need to find my t-value. So my degrees of freedom in this case is n minus 1, so 5 minus 1, which is 4. So it's going to be this row right here. And we want to use the area in two tails because we're calculating error bound, and error can be above or below the mean. So I'm going to take my error equals 2.776 times my sample standard deviation over the square root of our sample size, which is 5. That gives me an error of 13.3. And then I construct my confidence interval the way I would have before. Sample mean minus my error is less than the true population mean, which is less than the sample mean plus my error. Okay, and we use a Ttest distribution. It gives us a better, more accurate example. So I'm going to take 69.4 minus 13.3 is less than our mean, and 69.4 plus 13.3. So I get a confidence interval, a 95% confidence interval. That's important to note, right? Because we've got the area, two tails is 0.05. So this is a 95% confidence interval that we're calculating here of 56.1 is less than our mean, which is less than 82.7. So we've used our t-table to construct a confidence interval. So how do we do hypothesis testing with a t-distribution? So when the t-distribution is used for a hypothesis test of a claimed population mean, we're going to use a t-table instead of a z-table value. Okay? So we're going to switch from our t-table and use our z-table and use a t-table. With the t-distribution, instead of calculating a z-score, we have something fun and new to calculate, and that's going to be a t-score. Now, this should look oddly familiar to a z-score. The only difference is we use our sample standard deviation, because when we're using a t-score, we're finding a t-score because we do not know our population standard deviation, okay? But these two equations should look pretty similar. And again, n is our sample size, x bar is our sample mean, and s is the sample standard deviation, and mu is our population mean that we claim in our null hypothesis, right? Our null hypothesis is that there is no difference from the claimed value of the mean. So, for right-tailed test, we reject the null hypothesis if the computed statistic t is greater than or equal to the value of t found in the column labeled area in one tail. Okay, so we're going to only reject our null hypothesis if my test statistic, so the t I calculate, my t-score, is greater than the value of t. Okay? We will reject the null hypothesis if we're doing a left-tailed test and my t-value is less than the area to the negative of the value of t. Because as you saw, T-values are all positive in the table. Okay? And then for a two-tailed test, we reject the null hypothesis if the absolute value of the computed statistic is greater than or equal to the value of t found in the column. So absolute value meaning if I take the absolute value of -5, it's 5. If I take the absolute value of 6, it's 6. What absolute value does is measures how far a number is from 0. So -5 is 1, 2, 3, 4, 5 away from 0. And 6 is 1, 2, 3, 4, 5, 6 away from 0. Okay, so just a nice little college algebra refresher there for you. So let's go ahead and conduct a hypothesis test. Okay, we're still going to write our null hypothesis. We're going to write our alternate hypothesis. But then we're going to calculate a t-score. So listed below are 10 randomly selected IQ scores of statistics students. Okay, this one's you. No, you're 118. Oh, genius. So these data have the following sample statistic of n equals 10. So that's my population size. S is 5.2, and our sample mean is 109.5, okay? So using a 0.05 significance level, because that's the only one we can use for t-tests, test the claim that statistics students have a mean IQ score greater than 100, which is the mean IQ score of the general population. Look how smart you guys are. Okay, so my null hypothesis is that my mean is 100, right? There's no difference from the claimed value. My alternate hypothesis is that my mean is greater than 100. That makes this a right-tailed test, right? So we're going to go ahead and calculate our t-statistic. Remember, our t-statistic is our sample mean minus our population mean over the standard deviation divided by the square root of n. And I have all of these pieces of information. So I'm going to take 110, which was our sample mean. Nope, our sample mean is 109.5. Let me fix that real quick for us. My sample mean of not green. Okay, 109.5 minus 100 over my sample standard deviation, which is 5.2, over the square root of 10, because that's my sample size. And I get a test statistic of 5.777, okay? This is not the area under our curve. This is a t-test. This is our t-value. And I want my t-value to be greater than the t-table value. So why don't we go ahead to the t-table and find our t-value. So let's remember we're using a right-tailed test, so we just need the area in one tail. My sample size is 10, so my degrees of freedom is 10 minus 1, which is 9. Jumped ahead of myself there. So I go to my Z table and I find my degrees of freedom. That's 9. I scroll over to the area in one tail. So I get a test statistic of our t-value of 1.833. And because 1.833 is less than my computed test statistic of 5.777, we are going to reject our H naught at the 0.05 significance level. Let's say we take another 10 IQ scores from a randomly selected different class, and the statistics are as follows. So this is definitely not my class. You guys are too smart. So I find n equals 10. Our sample standard deviation is 5.2, and my sample mean is 9.3. So I want to compute, using a 0.05 significance level, that statistics students have a mean IQ score less than 100, okay? Which is the mean of the general population. So because it's less than, this is going to be a left-tailed test. Let's take a look at this. So I have, my null hypothesis is that there's no difference from the mean. But my alternate hypothesis now is that the students have a mean IQ score less than 100. So in my last example, I did a right-tailed test. Now this is a left-tailed. This is a left-tailed test. So we're going to go ahead and calculate our t-value. That's going to be my sample mean minus our population mean over my sample standard deviation over the square root of 10. And I'm going to get a z-value score, sorry, not a z-value, a t-score of negative 4.14. So I need to go to a t-table. I want to keep in mind that I reject the null hypothesis if the computed test statistic is less than or equal to the negative of the value of t found in the column labeled area and one tail, right? Because we're in a left test. So let's go ahead. My sample size was 10, so my degrees of freedom is 9. I computed a value. The test statistic that I computed was negative 4.14. And we're looking at the area one tail because this is a left-tailed test. Okay? I'm going to go down to 9. Go over the area one tail, I get 1.833. But because it's negative 1.833, because it's a left-tailed test, I need to look at negative 1.833. And I want my test statistic to be less than my critical t-value. So I have a critical t-value, negative 1.833. So because my critical t-value is greater than my computed test statistic, I can reject my H0 or null hypothesis at the 0.05 significance level.